Okay, chapter 3, quadratic equations and complex numbers. So solving quadratic equations is what we're starting with. Okay, so we can solve this in two different ways, really. One way would be to factor it, okay? So this is a difference of squares because this is a perfect square, right? And then I'm subtracting 25 from that, which is also a perfect square, so difference of squares, right? So if you remember the pattern, it's going to factor like this. Okay, and now I can use the zero product property. So if x plus 5 equals 0, then x would equal negative 5. And if x minus 5 equals 0, then x would equal positive 5, right? So there are my solutions, okay? So a lot of people, when they solve in this fashion, this is really the same thing, right? Because I could add 25 to both sides of the equation and end up with this. But a lot of times when people will solve this way by taking the square root, they'll just say, oh, I'll just take the square root of both sides, and then x is going to equal 5. Okay? But that's not quite correct. It does equal 5, but it also equals negative 5. When you take the square root of a whole equation, you have to take the positive and the negative root. So this is going to be plus or minus, okay? Because I'm going to get the positive root and the negative root. In other words, there are two different things that you can multiply by themselves to get 25, right? So if you think about it, x could be 5, yes, but negative 5 times itself is also positive 25. So there's a positive root, it's called the principal root sometimes, and a negative root, okay? All right, on to simple radical form. So if you think of the radical here as the squared root as a jail, here's how I explain this. If you want to get out of the jail, you need a twin. So I'm going to break up the 50. I'm thinking of any multiplication problem where the answer is 50. I don't want to use 1, but I want to find any other factors of 50. So I did 5 times 10, but you could have done 2 times 25. It doesn't really matter, okay? Now I can't break up the 5 any further. That's a prime number. All I could do is 1 times 5, and I don't want to use 1. But I could break up the 10 further, okay? So I could break up the, I already had the 5 out there. I could break the 10 into 5 times 2, okay? And now if you're thinking about this as a jail, well, hey, I've found a pair of twins. All right, so one of the twins is going to distract the guards and gets arrested and sent to a maximum security. Goes away. One of them is going to go away, but one of them will get out, okay? Okay, and then the 2, since it doesn't have a twin, is stuck in the jail forever. You got to have a twin to distract the guards, okay? All right, so let's try this one. So 200, I'm thinking 2 times 100. And then we could break up the 100 into 10 times 10. Okay, now I could keep breaking up the 10s if I wanted to here, but you don't need to break them down all the way. If you find twins along the way, even if they're grown-up twins, they can make a break for it, right? So one of those will distract the guards, and one of them will get out, and then the 2 is trapped in there forever. So 10 root 2 is simple radical form. Okay, you could either of these. This would be 7.1 or something like that. It's a little bit more than 7 because root 49 is 7, right? So either of those you could do a decimal approximation, but simple radical form is going to be an exact answer. Okay, so there we go. All right, so simple radical form, you're going to remove all the twins. Sometimes this. Hey, I don't have any twins down there. 1 times 3, so nothing wrong with that. But there's another rule. You can't have a radical in the denominator, okay? So when this happens, what if I don't have a twin for my 3, I want to clone a twin. So I can do that by multiplying by the square root of 3. And I can do that as long as I do the same thing to the top, because really I'm just multiplying this fraction by 1, right? It's just a different form of 1. So I'm changing its form, but I'm not changing its value, okay? So multiplying straight across, I've got 2 root 3 on top. On bottom, when it's root 3 times root 3, so you can put them under the same roof like so, And hey, now I've got twins, okay? So I can do this thing with the twins. So one of those will get out. And then there's no one left in the jail, okay? Or, you know, this is the square root of 9, which is just 3, okay? Now I'm not doing positive or negative 3 because I'm not taking the square root of both sides of an equation. I'm just taking the principal root when I'm simplifying like that, okay? And then I also still want to check to make sure that this is reduced. Some people might try to reduce the 3's, but one of them's inside a radical and the other one isn't, so you can't reduce those. But you would want to check these. 2/3 is reduced, so there's nothing else to do here. But say I had 6/4 in those positions, then I would reduce that to 2/3. So this is in simple radical form. Okay. All right, another method you can use. I could start trying to think of what times itself is 49/3. But this is easier to deal with if we break it up like so. And so if you have a fraction inside of a radical, you can do that, okay? And then, oh, square root of 49 is 7, right? I could break that into twins, but it's just going to be 7. Okay, and now I still have some work to do because I've got a radical in the denominator. So final answer is you'd never want to leave a radical in the denominator. It's just considered rude. Not sure why exactly, but it's just not done that way, okay? So then when I multiply straight across, now I've got my twins, and one of those can get out. So this is going to be 7√3 all over 3. Okay. All right. All right, so let's move on to these equations. So what I would do to solve these, we're solving for x. Since there's only one x term, I would just start to try to isolate x, right? So the first thing I would do is subtract 14 from both sides. Okay, then I'm going to divide by 2. Some people try to take the square root right now, but don't do that until you've isolated x squared. So I want to first divide by 2. Okay, now I can take the square root of both sides. And since I'm taking the square root of both sides of this, I want to make sure that I have the positive and negative root of 28. Okay, and then I'm thinking, kind of ran out of space here, move up here. I'm thinking, well, maybe there's some twins in there. So let's see if we can do anything more with this. So I'm thinking 4 times 7 equals 28, right? Or I could say 2 times 2 times 7. And hey, I found some twins. Okay. And so I'll see sometimes people will pull the 2 out in front of the plus or minus symbol, but you don't want to do that because really I'm just simplifying this, right? And that part is going to be 2√7. So the plus minus should still be in front. So I've got positive or negative 2√7 for my final answer. Okay. Same kind of deal over here on the next problem. I'm going to subtract 7 first. Okay, now I'll divide by 3. Okay, and then I want to take the square root of both sides. But hang on, nothing times itself is going to equal a negative number, okay? So this part is called the radicand. Okay, and when we get a negative number as the radicand, if we have a negative radicand, we're going to say no real solution. In Algebra 1, you'd probably just say no solution, but there are actually imaginary solutions, which we're going to get to in the next section. So I'm going to say no real solution. Okay, and I think I intended to do this one before that one. This is a simpler version of this. So, you know, taking the square root of both sides, but then nothing times itself will equal -9, right? 3 times 3 is 9. -3 times itself is also +9. Nothing times itself is going to be a negative number. I've got a negative radicand here, so no real solution. Okay. All right, moving on to the next page. Got some more quadratic equations to solve. So I'm trying to isolate for x. So what I want to do first is get the parentheses isolated. Okay, so I want to get rid of the 3/4. Okay, so one thing you could do is multiply the whole equation by 4 to clear the fractions. You can multiply both sides by 4 because then I'll just have 3 times the quantity x plus 1 squared equals 40. Okay. Now to get the parentheses isolated, next thing I'd want to do is divide by 3. Okay, and then that'll take care of the 3's. Now I'm down to x plus 1 squared equals 40 over 3. Okay, now a little shortcut for that. I haven't finished this yet, but honestly what I do on a problem like this, usually when I want to get rid of that, I'm going to want to get rid of that 3/4. So you can do that all in one step. Now on this next one you could multiply by 5 first and then divide by 2, but what I like to do is just multiply by the reciprocal of the fraction, because 5/2 times 2/5 is going to be 10 over 10, which is 1, right? So that will just take care of all of that. So you can just save yourself a step by multiplying by the reciprocal, but it works fine if you multiply first and then divide. Okay, I'll get back to that one in a minute, but let's finish this one first. So next thing I want to do is take the square root of both sides of the equation. Don't forget the positive or and negative symbol there. Okay, and then I'm isolating this for x. So I'm going to subtract 1 from both sides. Okay, and you could write -1 at the end after the radical, but it's not usually done like that. It can get a little confusing if you do that because it can be hard to tell if the -1 is in the radical or not. So it's just a lot clearer if you would put it in front of the plus or minus symbol. Okay, so I've got -1 plus or minus root 40 over 3. Okay, so I would be fine with this. We could actually take that a little further by simplifying this piece a little bit, because we could split that into root 40 over root 3. So let's go ahead and do that. Okay, and then I'd want to start looking for twins, and I'd want to get rid of the radical in the denominator. Okay, so let's see. I'm going to run out of space here a little bit. Okay, so 40 is 5 times 8, or I could think of that 8 is 2 times 2 times 2, right? Because it's 2 to the 3rd. Okay, so I can take out a 2 in the denominator. I'm going to have to move to the right here. And then I still have 5 times 2 up there, which is going to be 10. I'm going to simplify that to 10. Okay, and then I still have the denominator to take care of, so let's clone a twin for the 3. And you can put that 3 in right under the same roof, right? And down here, I'm going to have 3 times 3 under that roof. So, hey, I can take out twins there. There's nothing else I can do on the top. So let's see, 5 times 10 times 3, that's going to be root 30, 2 root 30 on top. And on bottom, it's just a 3. I can't reduce anymore. So this is another version of that same thing. Those would both be fine, okay, for me. Okay, so let's get to this example over here. I'm down to x plus 3 squared, and then think of that as 5 over 1 times 5 over 2, right? That's going to give me 25 over 2. I'll take the square root of both sides. Don't forget the plus or minus symbol. Okay, I'm going to subtract 3. So I'll slip that in front of the plus minus symbol. I'm also going to split this. Well, like I was saying before, I guess I would be fine with just this. But you could simplify that more by splitting the radical into top and bottom and seeing what we can do with that. I'm going to move over here just in case I need the space here. Okay, the square root of 25 is 5. Still got the radical to deal with though. Wanting a twin for the 2. So let's see, negative 3 plus or minus. This is going to be 5 root 2. And on bottom, root 2 times root 2. It's going to be 2 2's, so root 4, right? So this would work as well. Okay. All right, next up, the zeros of a function. These are the input values of a function that give an output value of 0. Okay, so the input values are the x's, and the output values are the y's. I mean, it doesn't have to be x's and y's, right? But that's the most common variables we have in these. Okay, so yeah, this is I don't have a y in this first function. It's an f of x, but we can think of that as our y. So our input's going to be the x, our output's the y. Okay, so it's the input value that gives an output value of 0. Well, here's my output value. So in other words, all I'm doing is plugging 0 in for y. Okay, so the zeros of a function, these are the x-intercepts. X-intercepts. That's all the zeros are. Okay, so I need to find the x that makes this true. So I just add 5 to both sides. So the 0 of this is 5. X equals 5. Okay. Over on this next one, I'm plugging 0 in for y. And then I'm going to solve this. So I'm noticing, hey, this is a quadratic trinomial. So let's try to factor it. Because it's already set equal to 0. And then if we can factor it, we can use the 0 product property. Okay, looking for two things that add to negative 4. Same two things multiply to negative 45. First thing that I think of when I see 45 is 5 times 9. That will work if the 5 is positive and the 9 is negative. Okay, so those aren't my zeros. That's just telling me how to factor this. Right? That's what goes in the back of these parentheses. And then I still want to use 0 product property. One of these two things has to equal 0. Okay, and there we go. Negative 5 or positive 9. Okay. All right, let's plug in 0 here. A lot of people get tripped up on ones like this. You could actually set this up with a diamond problem if you think of it like that, right? So, you know, the negative 8 would go on top and the 0 would go on bottom. But there's an easier way to do this. I've only got 2 terms, and they do have a common factor here, right? X goes into both of those. So just factor out an x, and hey, it's factored. And now it's ready for 0 product property. So either x equals 0 or x minus 8 equals 0. Okay, so there's my 2 solutions. Okay. All right, on this next one, I've got a 0 product property. I don't have a 2 product property. There's no such thing. So what I want to do, if this isn't set equal to 0, I want to set it equal to 0 right from the get-go. Okay, and now I've got a quadratic trinomial that hopefully I can factor and use the 0 product property. So there's no common factor here, right? Nothing goes into 3, -5, and -2. So I'm going to take the 3. I'm going to do a modified diamond problem here, or you can use other methods. I'm going to modify this problem by multiplying the 3 by the -2. Okay, now I'll do a diamond problem on this. Okay, multiplying, so, thinking you can do 1 and 6 or 2 and 3. Now, one of them has to be positive and one has to be negative. So it's tempting to use the 2 and the 3, but both of them would have to be negative to get the -5, and then it wouldn't work for the multiplication, okay? So I actually want to use the 1 and the 6. I want the 1 to be positive and the 6 to be negative. And then you can try it out, right? They add to -5, multiply to -6. So this is telling me this is going to factor into x plus 1 and x minus 6. Okay, and maybe I shouldn't have written the equals 0 here because we're just factoring this part of it right now, okay? So it's tempting to say, oh, -1, positive 6 are my answers, but we got to modify this answer back because we modified the problem, right? So in the beginning we multiplied by 3. Now I'm going to divide the number parts by 3. Okay, since I can't reduce 1/3, I'll pull the 3 out in front of the x. So I'm going to get 3x plus 1, and this is going to become x minus 2, right? 6 divided by 2. So I've factored this. Now this is all, well, I factored this actually. So this is all equal to 0. Now I can use the zero product property, okay? So if 3x plus 1 equals 0, then x is going to equal -1/3. Okay, and if x minus 2 equals 0, then x equals 2. And as usual, I ran out of space on my paper there, but there we go. Okay, and that's the end of that section. See you next time.